All right, this is Mr. McCord's chemistry class, unit 10. We're going to be looking at acids and bases, something that we've kind of brought up every once in a while throughout the course, but it's time to get into the nitty-gritty of it. One of the ways we decide whether a substance is an acid or a base comes from Robert Boyle, same guy that got us Boyle's law when we talked about the properties of gases. So there are some observable properties that can help us figure out whether something is an acid or a base. So some things that are noted that acids taste sour and they are corrosive. They're particularly pretty reactive with metals. They can change blue litmus to red. Litmus is a mixture of dyes that come from little plant material stuff. So this is an early form of an acid-base indicator that we will see kind of later on in this unit. You can make your own acid-base indicator with red cabbage. You can look that up online. Basically just a substance that changes color based on how acidic or basic the environment is around it. Okay, and acids also become less acidic when combined with bases. All right. On the other hand, bases tend to be slippery, like feeling on your hands. They change red litmus back to blue, and they become less basic when they're combined with acids. So there are some notable properties about how they felt, as well as how they changed this early form of a pH indicator, and they seem to kind of act against each other, like they canceled each other or something. Now, this definition is okay, but for some substances, whether due to their reactivity or their concentration, are not good for us to just put in our mouths and taste test or feel with our hands. That's not really, the best way to die as a chemist, is to just start sticking your hands in things and popping stuff in your mouth. So we would need kind of more stuff we can test with this. Other observable things about acids and bases to know include, don't taste the chemicals, include this stuff. So acids and bases both conduct electricity in water. We find acids a lot of times in food and drinks. Okay, and acids also have a pH range from 0 to 7. Our pH scale typically goes from 0 to 14. So we got kind of that range there. 0 to 7 is where we have our acids. Bases tend to be used for cleaning products like glass cleaners and plumbing, toilet bowl cleaners, things like that. And their pH range goes from 7 to 14. Okay, the further down the scale you go one way or the other, the more acidic or the more basic you get. So here's an example of the pH scale with some coloring that you might see on kind of a modern pH strip, or with a substance called a universal indicator that changes color for a lot of different pHs. So pH of 0 is very, very acidic. pH of 14 is very, very basic. And when they meet in the middle at 7, that is neutral, neither acidic nor basic. If you are moving kind of left on the scale, you're getting more acidic, right, more basic, and these work against each other. So as you have an acid and you start adding a base to it, it's going to start neutralizing it towards that value of 7. And if you keep adding more and more and more base, it's going to start bumping up into the 7-14 range and get more and more basic. If you add acid back into that, it's going to start lowering the pH back down to 7 until you hit the neutral point, and then continue to get more and more acidic if you keep adding acid to it. The most common way to define an acid or a base in chemistry is how the chemical breaks up to release certain ions in solution. Typically, it's going to be in water. So again, we're using the little AQ next to our chemical to describe kind of the phase of matter. AQ stands for aqueous, which means dissolved in water. So when an acid dissolves in water, it breaks up into ions. We call that process dissociation. So it dissociates, and the ions that it releases includes H+ ions. So, for example, when our HCl here dissolves in water, it breaks up into H plus and Cl minus ions. The Cl minus doesn't really do anything for how acidic or basic this is. It's just kind of along for the ride. But the H plus is what makes this solution acidic. Therefore, the more H plus that you have floating around in the solution, the more acidic it is. So the lower down the pH scale, the closer towards 0, farther away from 7 you would be. Okay. Now you may also hear H plus called something else. Sometimes we just refer to it as a proton. Now, way back with atomic structure, we talked about a proton being a positively charged part of an atom in the nucleus. If you think about it, H plus, well, has lost an electron, and hydrogen usually only has one electron. Now, also, hydrogen's most common isotope doesn't have a neutron either. So a hydrogen atom without an electron is basically just a proton. So an H plus is sometimes called a proton for that reason. So you might see that an acid is breaking up to release protons in solutions, or it deprotonates or something. Those are all just different words for saying it makes H plus ions in solution. Now, an Arrhenius base is the stuff that will break up and dissociates to make OH minus ions in solution. If you know your polyatomic ions, you will recognize that as hydroxide. So bases make hydroxide ions when they break up in solution, when they dissolve in water. Okay, so for example, when NaOH dissolves, it breaks up into Na plus and OH minus. Kind of like the Cl minus in the other example, this doesn't do anything for the pH. The Na plus is just kind of along for the ride, but the OH minus makes the solution basic. So it follows that the more OH minus you have floating around in the solution, the more basic it is, the higher up the pH scale you are for that solution, the more basic it is. Okay, so we look at H plus ions for acidity. We look at OH minus ions for basicity or alkalinity. Okay, now for acids, we typically have different names than what we would usually call something like this. So you might call this hydrogen chloride or hydrogen monochloride typically, but in terms of dissolving in water and becoming acidic, we call this hydrochloric acid. Now, thankfully, bases don't typically have a different name than usual. NaOH is usually read as sodium hydroxide, and we look at how it releases hydroxide ions, so we really just call it sodium hydroxide and stick to it. So acids are typically the only ones that end up with a different name. Okay, just to show another way that Arrhenius acids and bases kind of dissolve in water. In the past slide, we didn't show kind of the presence of water. We just said, oh, it's aqueous, so it's in water. When we take an Arrhenius acid and dissolve it in water and it releases H pluses, those H pluses don't really just stick around. After all, that is a tiny proton. It is a tiny charged particle that is going to be very attracted to all the electron clouds that are around it. So typically it gets grabbed up by water. Okay, so an H2O molecule that is dissolving the acid here will not really only just kind of break up the HCl and leave it as H plus and Cl minus. It will go and grab that H plus. So H2O taking on H plus makes it H3O, and it now has a positive charge from that proton picked up. So you'll sometimes see your H plus as H3O plus if we want to include the presence of water actually being there. Now, we're measuring the same thing either way. We're measuring how acidic the solution is by looking at how much H plus there is or how much H3O plus. But sometimes we just like to word it as that. It just depends on kind of chemist to chemist, textbook to textbook, problem to problem. So it's good to be able to recognize. We have a specific word for H3O plus as an ion. We call that a hydronium ion. So that gets its own name, kind of like hydroxide ions. Okay, but this means the same thing. If we're talking about the concentration of H plus or H3O plus in solution, that's just how acidic the solution is. Now, thankfully, again, bases are a little bit easier. They don't do anything special with water. The hydroxide does not get picked up by H2O to become H3O2 minus or something like that. It just kind of floats around on its own. Since the OH minus is, still pretty built as a molecule, even though it's charged, it's not just going to get suddenly grabbed by water. Now, of course, you can have other reactions happen with both acids and bases, and we'll get into those later. But specifically, this is just looking at what water does with them. Okay, so H plus is the same as basically H3O plus. We call that hydronium, and hydroxide doesn't really do anything special like that. Okay, now to cast a wider net to include the Arrhenius definition, but also some other things that slip through that definition that are acidic or basic, we have a definition from Bronsted-Lowry that talks about how something gives up or takes in H plus ions specifically. So if we look at an acid like HNO3, this is, you could call it hydrogen nitrate, or you could just say it's nitric acid. That's kind of the more common name. When nitric acid dissolves in water, this HNO3 reacts with the water, and rather than just saying, it breaks up into H plus and NO3 minus, we can also look at how that water takes that H plus and becomes H3O plus. Okay, so the thing about Bronsted-Lowry acids and bases is they typically come in pairs. If something is going to give away an H plus, something's got to be there to take it. And if something is going to take an H plus, something's got to be there to give it. So in this example, we have HNO3 giving away its H plus and not just throwing it out into the solution, but it gives it away to our water molecule here, our liquid water, H2O. So we have the NO3 minus left all alone, and water has picked up that H plus. Okay. Now this still kind of falls along the Arrhenius definition because our concentration of H plus has increased. We're getting more of this H3O plus in solution, which means we've had to have given off some H pluses. Okay, but more specifically, we're looking at something picking up that H plus. Okay, now for Bronsted-Lowry bases, this helps us kind of capture some more stuff that would otherwise avoid the definition. So if we look at something like NH3, NH3 is also called ammonia. It does have a special name. Okay, and it is basic. You can get a pH strip or a pH meter and check it, and it'll have a pH above 7. But it's not totally clear how it acts as a base. By the Arrhenius definition, it would have to give off a hydroxide ion, but it doesn't even have any O's in it, so it can't. Okay, but NH3 can increase the concentration of OH minus in water a different way. If we look at how it reacts with water, NH3 and H2O come together. NH3 takes an H from H2O to become NH4 plus. This is the ammonium ion. Okay, now what's left after H2O loses an H plus? Well, you got one less H and you've lost a positive charge, so we are left with OH minus, this OH negative, this hydroxide ion dissolved in water. So this is still a basic solution. We define the base as being the thing that takes the H plus from water to make the solution basic. So in this case, NH3 is our Bronsted-Lowry base. Now, I said before that Bronsted-Lowry acids and bases typically go in pairs. So if you kind of watch my color coding, NH3 takes an H plus from the water, okay, which means the water is giving away an H plus. So that typically makes it an acid. By this definition, it donates an H plus. So in this case, water is acting as an acid. Up here, H2O is taking an H plus to become H3O plus. So it's acting as a base. Okay, so some substances can be both an acid or a base depending on the situation they are put in. It's not always so cut and dry. We tend to look at common acids and bases as, oh, this is acidic. Like nitric acid is an acid, it's acidic. Okay, and sodium hydroxide is a base, it's going to be basic in solution. But there are some chemicals that can do either. Okay, it's not just an acid or just a base. It depends on what chemical environment we put it in. Okay. Now, also the Bronsted-Lowry acid-base definition helps us catch stuff that isn't dissolved in water, where we don't just see the H plus concentration rise or the OH minus concentration rise for acids or bases, respectively. So, if we're dissolving something in ammonia, in NH3, okay, in that liquid solution, we can still have a transfer of an H plus given away from something and taken by something else. So in this example, we put together HNO3 and NH3. Our HNO3 gives its H plus over to NH3, and we wind up with the leftover NO3 minus, kind of like what we had up here. We've also got this NH4 plus, kind of like what we had here. So we have an acid-base reaction going on here. We have an H plus being given away. So HNO3 is our acid giving up the H plus, giving up that proton. And NH3 is the thing picking up that proton. So NH3 is going to be our base. Okay. Now, on the right side over here, we don't have anything that is, we don't have anything that is H plus or OH minus floating around, so it doesn't look like our concentration of either is increased. But that doesn't mean that these aren't acids and bases. We do use water for a lot of our solvents in chemistry, but not always. So we have to kind of have a definition of acids and bases that works outside of water. And that's what Bronsted-Lowry is good for. All right, the last definition of acids and bases we're going to look at is the Lewis acid-base definition. Okay, and this again casts a wider net, but it still kind of fits into a lot of the acids and bases we see in the other definitions. Okay, so in this definition, a Lewis acid is something that accepts an electron pair to form a covalent bond in solution, whereas a Lewis base is a substance that donates an electron pair to make a covalent bond. So typically, we think of covalent bonds as shared bonds where something gives up some electrons, something else gives us some electrons, and they share them together. So there's a little bit from each atom that's coming together to bond. In this case, one substance is totally giving the pair of electrons to something else, okay? And just like with the Bronsted-Lowry definition, this means that an acid and a base go together. We can't really just have one or the other, because if something's given up the electron pair, something else has to be there to take it. Okay, the bond that we form, therefore, seems kind of wonky to say it's a shared bond because, yeah, they do end up sharing the electrons, but they both come from one thing. So you might hear this called a dative bond or a coordinate bond. Coordinate bond is kind of the more recent way to say it. It's kind of the more modern way. Okay, so in our example down here, we've got hydrogen ions, H pluses floating around, so something acidic. We've got hydroxide ions from bases, something basic, okay? And they're put together in a solution. So I have an acidic solution, I have a basic solution, I just dump them together, and we end up making H2O, okay? Well, to do that, these guys have to stick together and bond, right? An H plus and an OH minus. Well, our OH minus may have an extra pair of electrons to lasso over and grab this H plus and force to make a bond with it. And we end up making H2O. The positive and the negative charge cancel. We wind up making a bond across here, and so we get this H2O together. This is another example, again, outside of kind of that look of water. So in boron trifluoride and nitrogen trihydride, so boron trifluoride is this BF3, nitrogen trihydride is this NH3. We dissolve those in a solution together. BF3 and NH3 meet up, right? And they also bond together. So the NH3 gives a pair of electrons over to the BF3, makes a bond, and then they're stuck together. Okay? Now, looking at it in terms of a reaction equation is a little bit tough because it's not totally obvious just from looking at it that a bond's being made. What if this is just, attracting because it's a positive and negative and they just sit close to each other? How do I know it's a covalent bond and things like that? So it's best to look at this by looking at the electrons themselves. So if we kind of zoom in on this, here's our H plus and OH minus together. We've got our H plus and our OH minus. Our OH minus has all these valence electrons. So it gives up a pair to make a bond with the H+. So it forces that pair of electrons onto it. It keeps one, the H+ gets one, they share those two, and that makes this bond right here. Well, two H's, one O, all the charges cancel, this is water. Okay, so because H+ is what takes the electron pair, it's the acid. Our OH- or hydroxide is what gives up that pair of electrons, so it is the base. Okay, in our BF3 example, along with NH3, we've got our N with an extra pair of electrons that's whipping over and grabbing the boron. So we have a bond across here. Okay, so again, boron is what takes the electron pair. It's what's being bonded to. So that makes it the acid. Our NH3 is our base. It is what forces and makes the bond by giving up, donating its electron pair. So our NH3 is the base. Okay, so some of this stuff hasn't really changed. H+ is still talking about acids. OH- is still talking about bases, and that works in this definition. Okay, we said NH3 was a base before because of how it could pick up an H+. Well, it can also pick up other stuff like BF3. And so this just makes it a base under a different definition. Okay, and let's look at this last one here, where we kind of take a little bit from each. So our H+, our acid before, is now also picked up by NH3 to make NH4+, which is something we saw in the Bronsted-Lowry definition. Okay, so this works here too, to make that ammonium ion. Okay, so these are just a couple different ways we can tell whether something's an acid or a base. If you're doing the Lewis acid-base definition, look for a new covalent bond. Look for stuff sticking together. Okay, so if you have something like H+ and OH- separate, they come together to make one thing. They synthesize together. Same thing over here and over here. So that's kind of your giveaway for something being a loose acid or base.